Good evening, everybody. Welcome to Chem 1211 with your host, me, Dr. White. And tonight I will be going through Quiz 5 review. Don't forget, this Thursday I will be giving Quiz 5. You'll have until Friday to hand it in 8 p.m. Now, don't forget the following week is Thanksgiving. And on that Wednesday, I will give quiz 6. But you're going to say, wait, the school's closed for classes, yes. But because it's Thanksgiving, I'm going to give it on Wednesday morning, but you'll have until the following Monday, which school is open, to finish quiz 6 and hand it in by 8 p.m. All right, let's get going. But before I do that, let me remind you quiz 5, like I said, will be on Thursday the 21st. That's when I'll send out the password for the PDF file. Earlier, you'll have until Friday to hand it in, 8 p.m. Quiz 5 has 9 problems, including some multiple part, but no multiple choice. And it's worth 50 points. And it will cover chapter 15, chemical equilibrium, and the collision theory of reactions and rates of reactions, chemical equilibrium. And it's time for Dr. White to use his North Side Chicago French accent, the Chatelair's principle, which is not really how you pronounce his name. But I'm from the North Side of Chicago, so that's how I'll pronounce it. I was just looking, this is an older review. I still have cursive. Sorry about that. I'll read it slowly. Name one of the key factors in the collision theory. By the way, where I'm reading is located in the lecture section of Blackboard for Chem 1211 NET 04, and it's cleverly named. Oh, it's the wrong thing. This is in the problem section. Let me get the right thing. There we go. This is not handwritten. He used to handwrite all these. All right, let's get going. You should know the collision theory and the 3 key elements of the collision theory. In order for a reaction to happen, molecules must collide. Colliding molecules must have a minimum amount of energy. It's called the activation energy for a reaction to occur. And finally, for certain molecules, the orientation must be correct. Sort of like putting the key in a lock. If you have it upside down, it won't work. At least mine don't. All right. And the reaction rate is the rate in which products are made or reactions are consumed. Now, you should know what are some factors that influence the reaction rate. Well, the physical nature of the reactants. Are they a solid, liquid, or gas? Gases react the quickest, solids the slowest. All right, now, how much the concentration, which is how much of the reactants do you have? The higher the concentration, the more collisions, the faster the reaction rate. And now, do you think this might be important right here? I'll be subtle. Can't know this. And there's an important rule of thumb. And a rule of thumb means it's true about 99% of the time, but never 100%. And that is the rate of a chemical reaction doubles for every 10-degree increase in the reaction temperature. Now, another thing that will influence the reaction rate is the catalyst. And you should know, how does a catalyst work? And that works by lowering the activation energy. So you need less energy for the collisions for reaction to occur. Now, when we talk about reactions, an important way of showing this are the energy diagrams. And there are two types of energy diagram. One is for an exothermic reaction where heat is given off. And an endothermic reaction where heat is added. And you should know how to do the energy diagrams for these. I'll show you, it's in the problem set, and I'll do one a little while. You know something? Let's do one right now. We'll look at one. Now, here's the energy diagram for an exothermic reaction. Heat is on the right side. This is called the Haber-Bosch reaction, and this reaction affected this planet greatly. It allowed farmers to grow more food, increase the population of our planet, and unfortunately, it allowed companies to make cheap explosives, which led to longer and more devastating wars. There's good and bad in a lot of things. Now, there's a principle called conservation of energy. You never destroy or create energy. So the total energy on the left equals the total energy on the right. Now, the total energy on the left is the energy of N2, nitrogen, and hydrogen gas, right here. Now, on the right, the total energy is ammonia and H3 and the heat. But the heat is lost, so the energy of the products, chemical products, in this case ammonia, is less than the reactants N2, H2. And in the energy diagram that you should know how to do, hint, for an exothermic reaction, energy on the Y, time on the X, you start here, you go over the hill and down the hill to grandmother's, so anyways, to ammonia, which is lower. And you should know that the activation energy, abbreviated EAC, is from where you start to the top of the hill. Now, for an endothermic reaction, again, the energy on both sides is the same. But on the left side, water has less energy than the chemicals on the right because some of that energy is released by heat. Oh, I'd like the special effect. Never mind. Anyways, so water will have less energy, remember Y energy X time, than the hydrogen oxygen, which is higher energy. And the activation energy is from where you start to the top of a little hill, which you have to do to get to the products. Now, in a reaction, which I just showed you, but we hadn't talked about it yet, that's called a chemical equilibrium. A chemical equilibrium is a reversible reaction. And you know you have a chemical equilibrium when you see the double-headed arrows, one arrow going this way and the other going the other. And what this tells you is A plus B react to make C plus D. But also C plus D react to make A and B. And that's what we mean by reversible. It goes back and forth. Now, important thing to know about chemical equilibrium, and that is the forward and reverse rates of the reactions are the same. And we say at equilibrium, the forward and reverse reaction rate of reactions are the same. Now, there's an important number that you can calculate from an equilibrium reaction, and that's called the equilibrium constant, K sub EQ. And if we had a reaction, W moles of A, X moles of plus X moles of B, make Y moles of C plus Z moles of D as an equilibrium, the equilibrium constant is the concentration of the products, and that bracket means moles per liter C to the power, which comes from the coefficient of C, times, not plus. Students like to put a plus here. No, because they see a plus up here. No, it's times the concentration of the other products to the power of the coefficient. And it's divided by the concentration of the reactants times each other to the power of the coefficient for each reaction. Like the coefficient for A is W. So it's this reaction concentration to W power. And if we look at 6A, write the equilibrium constant for this reaction. The two products are sodium and A. So we put in the brackets, the coefficient is 4 times oxygen, O2 in the brackets. Now, when there's no coefficient, that means 1, which is what I have here. You don't show it. Now, it's divided by the products, the reactants on the left, sodium oxide, and notice the coefficient is 2, so it's the second power. And I have other examples here too. And remember, when we put it in brackets, that means moles per liter concentration. Now, the equilibrium constant KEQ tells us how complete or which way you have in an equilibrium. Which do you get more? When you mix these together and it's at equilibrium, are there more reactants or products? And you should know the larger KEQ is, the more products there are. The smaller it is, less than 1, the more reactants. If K equilibrium, and this means in math, much greater than 1, the concentration of the products will be greater than, this means greater than, the concentration of the reactants. if KEQ, the equilibrium constant, is much less, that's what this means, than 1, the opposite is true. The concentration of the reactants, how much of the reactants is greater than the concentration of the products. And if we look at number 7 from the Chapter 15 practice problems, predict the relative amount of reactants and products for the following. And here we have 2HCl, hydrochloric acid, in equilibrium with hydrogen and chlorine gas. And the K equilibrium is 2.0 times 10 to the 4th. Well, that's much larger than 1. By the way, these 3 dots is from math, and I like using them whenever I can sneak them in because I just think it looks cool. Dr. White always tries to be a cool dude. Therefore, the concentration of products is much greater than the concentration of reactants. Now, if we look at this number for the B, 2 nitrous oxide decompose to make nitrogen gas and to an oxygen gas. K equilibrium is 3.2 times 10 to the minus 34. And since the equilibrium constant is much, much less than 1, therefore, the reactant's relative amount, concentration, that means that's why we put it in brackets, is greater than the amount of products concentration. Now, when you have an equilibrium, there's a very important principle, and I'm going to use my Chicago North Side French accent. That's Le Chatelier's principle. Now, it states an equilibrium shifts to the side to reduce the stress put on an equilibrium. I will never ask you what's the definition of Le Chatelier's principle, but I expect you to know how to use it. And where do you need to use it? What happens to the equilibrium or the concentration of certain reactants or products if you change the concentrations of certain things in that equilibrium? Also, what happens when you change the temperature for an exothermic reaction and for an endothermic reaction? And one thing I need to tell you is if you put a reaction in a boiling water bath, you're adding heat. That adds heat. If you put a reaction in an ice bath, that removes heat. All right, let's look at number 11. This is for an endothermic reaction. Oops, the plus fell off here between water and H, the heat. Don't look, no plus. Oh, Anyways, the question is 3 points each. What happens to CO concentration and H2 concentration if you put the reaction in an ice bath? Well, ice bath removes heat. At equilibrium, there is a certain amount of heat. And now you've removed some. And the reaction says, oh no, we need to fill up, replace that heat. So how can it make heat? By reacting CO2 and hydrogen and going to the heat. Well, when you react something, you consume it. There's going to be less. So to make more heat, you have to react CO2 and hydrogen is consumed, there's going to be less. The concentration decreases. Now, when you make more heat going this way, you will make more water and more CO. And when you make more of something, the amount you have, the concentration increases. Now, let's look at C. What happens when you add more carbon dioxide to this reaction? Well, at equilibrium, there's a certain amount of carbon monoxide, CO, water and heat, and CO2, carbon dioxide, and hydrogen. But now you've added CO2. Oh no, we have too much CO2. We've got to get rid of it. How can you get rid of it? When it's consumed in the reaction of CO2 and hydrogen going this way to make more heat, water, and CO. So CO2 to reduce the level, consume it, reacts with hydrogen. Hydrogen is being consumed, so that will decrease. And since we're going this way to get rid of the excess CO2, we're making more heat, more water, and more carbon monoxide, CO. When you make more of something, the amount you have increases. And that's how you use Le Chatelier's principle. Nope, your hair doesn't work on that. By the way, your lungs, and I believe your liver, but don't quote me on that, work on Le Chatelier's principle. And a version of Le Chatelier's principle keeps your blood at a certain measurement of a certain important parameter, which we'll talk about in next chapter we cover. So with that, I'm done for the review for quiz 5 that I'll be giving this Wednesday. I'll stick around. If anybody has any questions, feel free to ask. One last public service announcement from the management, me, is don't forget, I posted the extra credit project, 10 bonus points. Let's see if I can find that. Nope, that's not what I want. That's what I want. And right here, there's an assignment that's extra credit, and that's 10 bonus points. You have until November 27th by the end of the day to hand it in. Now, there's a video I have that you can see in the assignment area. And as a special public service to you, my students, before you hand it in, email me, don't hand it up, upload it to Blackboard, email it to me, I'll check it. If there are things wrong, I'll get back to you and tell you need to fix this and give you some hints, or come to my office hour. And with that, I'm done. I'm going to stick around for a little while. Anybody has questions, stick around and I'll help you out. If not, I'll say gehen gesund, which means go in health in Yiddish, And you know what I'm going to do next. Bye now. Bye. I stole that from Granny to Beverly Hillbillies. Bye.